Per un attimo esco e entro di nuovo nella aula. Ecco, è iniziato. Meglio tardi che mai. Allora, questa è la registrazione della prima parte della lezione di 28 ottobre, in cui cercheremo di ritornare di nuovo allo studio qualitativo dei sistemi 2x2, e di vedere per vari esempi quale tipo di atteggiamento abbiamo vicino di questi punti di equilibrio. Per il momento vorrei solo ricordarvi quello che ieri abbiamo studiato. Si trattava di, prima di tutto si trattava di passare all'inglese. Ok, let us switch to English. Then let us remind what we had done yesterday. So we practically had one case of two eigenvalues that have been real eigenvalues, but with opposite sign. When we have real eigenvalues with opposite sign, then we put special name. We call this saddle point, zella in Italiano, and therefore our first case was lambda 1 was the first eigenvalue. That was one of them was, I think yesterday, negative. Lambda 2 was positive. So in this case, we have saddle point. I shall put on the right-hand side small picture to remind you what does it mean, saddle point. Zella means more or less such thing. You have in one direction behavior like this, in the other direction behavior like this, because this is the zella del cavallo. Therefore, this is why it is called saddle point. In Italian, this is very clear that in one direction you go like this, in the other direction opposite behavior. And let us make our small picture to remind you what does it means zero, because we translated everything, the critical, the stationary point, punto di equilibrio, we have shifted to the origin. And the picture was the following, more or less. Remember, we had such behavior. And for example, when lambda 1 is negative, this means we are on y1, y2. In this direction, the arrows was, in this case, approaching the origin, because this is a to the power lambda 1t, the solution. And this solution obviously decays. And then the arrow were approaching from the left and from the right due to this sign, while in the direction 2, we had opposite. Everything escaped. And therefore, these two lines enable us to draw the arrows also on the curve. So in order to have this continuity argument, to have similar thing, it is clear that here our arrows shall follow what happened on the axis. Therefore, we have such behavior, and here we have such behavior. This is to remind you what is the meaning of saddle point. One is negative, the other guy is real and positive. Then we had yesterday another case, lambda 1, for example, positive, lambda 2 positive. And in Italian, it was called nodo, in English, knot. Therefore, we have, you know, in the sea, when sailors use ropes, then they make with the rope different knots. And these knots, this is the origin of this word, nodo. And we have, in this case, very simple node. And let us make here the picture. So what we have? First of all, both are positive. This means in all axes we escape. So our arrows are like this, and here like this. Here we escape, and here we escape. Here, escape from 0. And then we have these curves in general. And the arrows follow our axis. So they are like this. They escape. And we can say in this case, if somebody asks you, your stationary point is stable or unstable? Stable means trajectories approach the point, unstable, they escape. In this case, we have really very unstable stationary point. This knot is unstable. It is not stable. Not stable. Or you can say unstable. Instability is one of the important things we shall, for example, apply for our concrete models in biomedicine. Then we had the other thing, the case of stable knot. I shall use, forgot to take colored. Lambda 1 negative, lambda 2 negative, then the knot is stable. What you have to do? The same picture, so only you invert the arrows. So your arrows approach 0, and we can make this small picture here, again like this, to remind you only. So we have such behavior. Arrows approach. And we have stability, which is very important and very nice property. This means that our system is not destroyed very easy. This was the case of real eigenvalues. Of course, it is possible to consider limiting cases. For example, if one of these guys, lambda 2, is 0, you can solve directly our system that we already put in which form. We had zeta 1 prime is lambda 1 zeta 1, zeta 2 prime is lambda 2 zeta 2. So this is very simple system, and if you consider this system and the solutions, you can build these pictures, but I strongly suggest to remind in our lecture notes, you shall see the pictures. It is much easier to connect case of eigenvalues with concrete picture, because in this way you shall avoid complicated calculations to find exact solutions. You simply find eigenvalues, and you see how they behave. So when we have real eigenvalues, these are our pictures. We can put here case of real eigenvalues. And today we shall start an example where our eigenvalues shall be purely complex, or they shall have real and imaginary part. So I plan to clean now the blackboard. If you already put in your notebooks, and let us go now to the case of 2 by 2 matrix for which okay, this is very good. Okay, for the moment we shall use this. In the break I shall find something to make it better. So actually we had, no, they didn't give us this thing. Okay, this is sufficient. Now we have the case of complex eigenvalues. We can immediately say that when you have complex eigenvalues, then you shall we shall speak about in Italian fuoco. Fuoco in English I found translation focus, and this focus is connected with the case when we have complex eigenvalues. So let us take our example. So we have epsilon1 prime shall be, let us put epsilon1 minus epsilon2. And epsilon2 prime shall be epsilon2 plus epsilon1. This is similar to the example we studied yesterday. Actually, our example from yesterday, this coefficient here was 0, and this coefficient was 0. So I added these two guys a little bit to see, and if you prefer now to compare with yesterday calculation, let us put here a coefficient that shall vary. We can take this A0, this shall be example from yesterday. We can take A positive or A negative, and we shall see what kind of fuoco, what kind of focus we have in this case. Actually, we can find for this system, obviously, if it is linear system, always we know that stationary point is 0, because if you have to solve this right-hand side equals 0, then obviously one solution is epsilon equals 0. Therefore, it is natural to consider a stationary point that is epsilon 0. And in our case, we have really to see what is our matrix A. In this case, the matrix A is very simple. We have first parameter A, then -1, then we have 1, and then we have A. Let us see if you agree with this definition of the matrix A. And now we have to find the eigenvalues of this matrix. So we consider A minus a lambda identity matrix. This means on the diagonal I have to subtract lambda. So this matrix is A minus lambda minus 1, 1, and here we have A minus lambda. For this matrix, to find the eigenvalues, we have to take determinant. determinant equals 0 is our characteristic equation. Therefore, we have to take determinant of this guy, determinant, and take this determinant equals 0. We know that this equation is a characteristic equation. L'equazione caratteristica is this one. And here this determinant is quite simple. This by this minus this by this. So we get this is a minus lambda squared plus 1. We have this equation. And of course, this equation we can solve very easily, because if I put 1 to the other side, I shall get the relation a minus lambda, or if you prefer, probably it is better to write directly lambda minus a square equal minus 1. Before, when we couldn't use complex numbers, we know that this equation has no real solution. But now we have the possibility to take square root of minus 1. What is square root of minus 1? If you take square root, what is the numbers such that the square of this number gives you minus 1? Of course, this is I, imaginary unit, but this is also minus I, because minus I squared is I squared. Therefore, this equation has two solutions, zeta equal plus minus I. And we can apply this fact and find, now we can say our solutions are not real, but complex. So if you use for zeta this expression, lambda minus I, we can say that probably here I still have some space. May I write? Can you see from there this line? So from here I write instead of zeta lambda minus 1. So lambda shall be A plus minus I. This I obtain substituting here zeta with lambda minus A. I know A, therefore I put on the other side minus A becomes plus A. Therefore my two solution, lambda 1 is A with sign plus I, and lambda 2 is minus I. Sorry, A minus I.
Sorry, Professor. I
Please.
didn't get the substitution. Why that?
This you can understand?
That equal to?
Plus minus I.
Okay.
This you understand because we have zeta square. Let me explain you better. So here we have zeta square equal minus 1. From this I get zeta plus minus I, two roots.
Yes.
Okay. Then I compare this equation with this equation. They are very similar. Therefore, I shall call this guy zeta. This is my zeta. And if I plug here, I shall have lambda minus A equal plus minus I. Because this is my zeta. I apply this relation. And I get this identity. And now I simply put minus A on the right-hand side because I know A and I am looking for lambda. That's why we put a to the right-hand side, so we get from here lambda is equal a plus minus I. This is the same relation like this, only I put a on the right. And this means that we have two roots, plus I and minus I, that I have written here. So this is the procedure to arrive to these relations.
Okay, but why we pass from a minus lambda to lambda minus a?
Because this is a minus lambda square. When you have the square, you can put under the expression any sign, plus or minus. You have this property. W square is, can you see here? Or this is a little bit out. If you put W square and minus W square, they're always equal.
Okay.
So if you put minus, then you exchange the a minus lambda becomes a minus lambda is lambda minus a with sign minus. So we have this relation, and that's why the minus is not seen when you take the square.
Okay, thank you.
Okay, welcome. Other questions? Because now we have to find the solutions. And the last time we used a kind of very particular choice. We constructed from epsilon 1 and epsilon 2, we constructed one complex valued zeta. So what was this zeta that we used yesterday? We simply took, here there is a little bit space, we take epsilon 1 plus e epsilon 2 shall be our new zeta. The purpose is to find the equation satisfied by zeta and solve it. Of course, when a is 0, yesterday we made the calculation, but today we shall make for any a, because this is the same calculation. So if you take zeta to be this guy, then we can find the derivative of zeta using our system 1. So how we shall do this? I think here I have a little bit space, so I shall write this, the equation for zeta prime on the left of 1. Let us compute zeta prime. This is epsilon 1 prime plus I epsilon 2 prime. This is the usual derivative. We take the real part, differentiate, take the imaginary part, differentiate. And now we use our equation. So this is equal a epsilon 1 minus epsilon 2. This is epsilon 1 plus I, and then we have a epsilon 2 plus epsilon 1.
I'm sorry, Prof. I can see there.
You are right. Let us do small.
Thank you.
Now it's okay. Okay, thank you for this. Now we shall group these expressions. So on one hand, we have this guy and this guy. As you can see, if I take for this guy and this guy one common factor shall be a. What we shall have? This is a times epsilon 1 plus e epsilon 2. This is taking together these two guys and putting common factor A. And the other guy, yesterday, we already discussed. So this was minus epsilon2 plus I epsilon1. What we have done for this factor, we put for this term, we put as common factor I. If we put I in front, then we shall have A. Remember that epsilon1 plus I epsilon2 was exactly our zeta. Therefore, I shall substitute this guy with zeta. And now we take plus I, and then we have, as yesterday we did this calculation, this guy. Let us check if my calculation is correct. If I put I by epsilon1, this is exactly this guy. So this is correct. This by this gives this. If I put I times I square is minus 1. So this is exactly this guy. So we can say that this is finally A plus, let us write A zeta plus E zeta. This is our final result. The derivative of zeta is this guy. We have zeta as common factor. And this is very crucial for our equation. Thanks to this calculation, let us call this calculation 2. Now we can use calculation 2 and write here the equation satisfied by zeta. What we have? Zeta prime shall be A plus E times zeta. And this is very simple equation because we said we can work with complex numbers exactly as we did with real numbers. So what is the solution of our problem 3? If you for the moment forget about the fact that this is complex number, whenever you have, for example, zeta prime equals some number mu times zeta, how you shall find the solution? You know very well the solution when mu is real. But I am saying that solution is absolutely the same when mu is complex. Nothing changes. So we have to write zeta, our zeta as solution, depending on t, shall be a to the power mu t times our initial data zeta 0. Everything here has meaning because we know very well what is a to the power complex number, because this we already discussed when we had this theory with complex numbers, and now we shall see how we can simplify this guy. We shall do this only once, but after this you shall use only the conclusions of this calculation. You shall not repeat every time when you have a concrete example or some problem for the written exam. We have to check what is the eigenvalue, and this is crucial that we already have found eigenvalues. A plus minus E. So we have complex part, imaginary part, and we have eventually real part of our eigenvalue. But this is crucial now in order to find the solution and build our picture, epsilon1, epsilon2, because our zeta is defined by real part is epsilon1, imaginary part is epsilon2. So from 3 we deduced 4. This guy. And now I shall try to see what is the real part of zeta, what is imaginary part of zeta, and we shall build the picture. But since I need a little bit space, I shall leave 3 and 4, and then I shall clean everything remaining in order to calculate y1 and y2. Before cleaning, let me ask you if you have some questions, please.
The expression for the like that I y with 1 plus e, right? Not the initial expression for the
This one.
Yeah, it's given. Like I did not.
This is important. This is given by me in order to have more direct calculation, more explicit solution. This is a trick that we use when we have complex. It is called so-called complexification of your system. Instead of writing 2 by 2 system with complex number, you write in very compact form, and then you write the solution very easy. Another question, other questions if you have? So the question was from where this is coming. This is what I put as set. I introduce this quantity zeta that is useful to find y1 and y2. Okay, so let us clean, make this calculation, and then make a break. I think with this week, our first part of the course, the deterministic part, is shall be over. From the next week, slowly, we shall start with a little bit probability, statistics, and shall try to have again less theory, more examples. Okay. Here, the only thing I need, the expression for mu, this was A plus I. This was our mu, because exactly, this is 3. So, how we shall express? We know that zeta 0, you see here, okay, zeta 0 is y1 0 plus e y2 0. This is due to this definition. When you take t equals 0, you put initial data that I called y1 0, y2 0. Remember that if we want to build our picture for y1, y2, we know very well that complex numbers, they are very well associated with the plane. And therefore, we start with some point that is y1 0, y2 0. And we want to see how the solution behaves. What is the solution? So this is given. These are our initial data. We have to take the expression a to the power a plus e t, and we want to multiply by zeta 0. This expression is exactly the solution that we already proposed. So I have to put in this expression the real and the imaginary part. So what we have, this is probably, this is stupid idea to put so on the left. Let us put here from here. Okay, this is C. So we have a to the power e, a plus e times t, and then we have zeta 0. Now I am using the definition of this exponent. So this is a to the power at times a to the power et, because whenever you have exponent and the exponent you have sum, this is a first exponent, a the second power, times zeta 0. I replace it, y1 0 plus y2 0. Now I am using trigonometric representation a to the power et. What was a to the power et? A to the power et, remember in complex numbers, we use this. This is cosine of t plus e sine of t. This is the trigonometric representation of complex numbers. And I substitute. So we have a to the power at is the same. Then we have cosine t plus e sin t. And then we have y1 0 plus e y2 0. Now we shall try to make assumption that shall simplify our calculation. To simplify our calculations, we shall take this point zeta 0, not here, but we shall put, for example, on the x y1. This shall be much simpler because y2 0 shall be 0, and we shall have less calculations. Let's see what will happen if we have this guy. y1 0 is the first coordinate, and this is the second coordinate is 0. So we are trying to see starting from point on the x y1 to have less calculations. Of course, we could take also initial data on the x y2. The situation is similar. We take one of the possibilities. And if this is the case, if we take this equals 0, then this guy here automatically disappears. But then we have immediately what is the real part of this expression. As you see, this is real. A to the power at is real. So I have to open the brackets and we get a to the power at cosine t y1 0. This is when I open the brackets, this by this by this. And then we have imaginary part, that is plus I a to the power at sine of t y1 0. So, as you can see, a real and imaginary part, they are very simple. And having in mind that our zeta is y1 plus y2, we can immediately conclude this is y1 of t, and this here is y2 of t. And we can write our solution. So what is the solution? y1 of t is a to the power at y1 0 cosine of t. y2 of t is a to the power at y1 0 sine of t. And now I am ready to build the picture. But you can see that the picture actually has three different cases. One case is when A is 0. So first, let us build the case A equals 0. If A is equal 0, what you have? This guy is 1, and this guy, a to the power 0, is 1. So this is 1 and this is 1. So what we have? Constant time cosine of t, constant sine of t. As you know, and we already yesterday mentioned this, cosine square plus sine square is 1. Therefore, this point, when A is 0, is exactly point on the circle that is epsilon1 square, when you take epsilon1 square of t plus epsilon2 square of t shall be equal to what? We have epsilon1 0 to the power 2. Why? Because when you take cosine square plus sine square, this is 1. So we have this equation that epsilon1 square plus epsilon2 square is a constant. But epsilon1 square plus epsilon2 square is a circle. And this circle is exactly the circle that is defined by epsilon1 square plus epsilon2 square equal this point, epsilon1 0 square. So we have this circle. If I take another epsilon1 0, you can see smaller epsilon1, I shall have another circle. And so on, we have such circles that determine our solutions. These are our solutions. They are closed curves, they are perfect circles, and this is specific case when A is 0. Remember that this picture is for A equal 0. Now I propose you to make usual break, and after the break to have very short activity, because yesterday I have stolen 10 minutes, therefore today I have to give back a little bit of time. So we shall have short, first we shall finish this picture when A is negative, A is positive, and then we shall eventually put another example without making this long calculation. This is once we are doing these calculations, and then we shall use directly the picture. Okay, I leave for you the break to prepare some questions, and after the break we shall try to answer you. Now I shall stop the registration, and we are starting.